Hey everyone, how it goes, and welcome back to Computer Science 311. Today, we're going to discuss operating system services. In the last lecture, we started discussing what is an operating system, and we didn't really come up with a good definition. Now, an operating system provides the environment within which programs are executed. What we're going to explore is the design of a new operating system is a major task, and it's important to keep the goals of the system to be well defined before you ever design it. Now, we can view an operating system from several different vantage points. One of them focuses on the services that the system provides. Another is the interface that makes it available to the users and the programs. And a third is its components and their interactions. We're going to explore all of these aspects of an operating system and show each one of the viewpoints from the user, the programmers, and the operating system designer. The operating system provides an environment for the execution of these programs. It makes certain that certain services are available to the programs and to the users of those programs. There's a variety of different services that an operating system can provide. However, we can start identifying each of the common classes that they should have. Now, one perspective that we're going to first view is from the user. So, what services are provided to the user? Well, first of all, you should have a user interface, and almost all operating systems have some sort of UI, user interface. This can vary between like a command line interface, a graphical user interface, touchscreen, and batch. Another service is program execution. The system must be able to load a program into memory and then run that program. Another is I/O operations. A running program may require input and output, which may involve a file or other I/O devices. File system manipulation. Obviously, programs need to read and write files from directories. They also need to create and delete them by their name, search for a given file, and list the file information. Some other services from the user perspective are communication. Now, there's a lot of circumstances in which one process may need to exchange information with another process. Communications happen in between these processes that are executing on the same computer or between processes that are executing on different computer systems that are tied together by a network. Communications can be implemented via shared memory or in another technique called message passing. Users also expect error detection. The operating system needs to be able to detect and correct errors constantly. And errors can occur in the CPU, the memory, the hardware, I/O devices, and all sorts of places. Now, for each one of those types of errors, the operating system should take the appropriate action to ensure correct and consistent computing. Another perspective that we have to look at is understanding that the operating system function has to ensure the efficient operation of the system via its resources. One service from this perspective is resource allocation. There are multiple processes running at any given time, and resources have to be allocated to them. The operating system can manage many different types of resources, such as the CPU, the main memory, and file storage. Another important service is called logging. We want to keep track of which programs use how much and what kinds of computer resources that it uses. This record keeping may be used for accounting or simply for accumulating usage statistics. We mentioned this in the previous lecture, but another very important service is protection and security. Now, we have to distinguish the two. Protection involves ensuring that all access to the systems is controlled. It protects the operating system. Security of a system involves protecting it from outside invaders. Here's a view of some of the operating system services. As you can see here, we have the user elements right here, then a layer called the system calls, and here are the different services that they provide. Now, going into each one of these parts a little bit further, you do have something called a command line interpreter that is a user interface. This allows direct command entry, so you can think of this like the command line. Now you can also have a graphical user interface where the thing is, you have graphics that represent these ideas. These are called icons that represent files, programs, and actions. This was invented by Xerox. And many systems include both a command line interpreter and graphical user interfaces. Going into a little more detail, system calls provide an interface to the services that's made available by the operating system. These are typically written in a high-level language like C++. Now, these system calls are mostly accessed by programs via a high-level application programming interface, otherwise known as an API. So an example of like a system call is if you have this source file that then goes to a destination file where we are copying the contents from one file to another. These are all of the system steps that are required in order to do that. Now typically, there is a number associated with each one of the system calls. A system call interface that serves to link together all of the system calls are made available by that operating system. The system call interface interprets the functions and calls them in the API, and that evokes the necessary system calls within the operating system. The caller of this doesn't need to know how the system is implemented, they just need to know what it does during execution. Here's how a user application can interface with a system call interface in order to access some of those system commands. Now we also have to consider that we need to pass parameters when we are evoking these system services. Now there are three general methods that are used to pass parameters to the operating system. The easiest approach is to pass the parameter in registers. However, in some cases there may be more parameters than there are registers. In this case, the parameters are generally stored into a block or a table in memory. Another approach is parameters can be placed or pushed onto a stack by the program and popped off the stack by the operating system. Some operating systems prefer the block or stack method because those approaches do not limit the number or length of the parameters being passed. Here's an example of how a user program can load a parameter into a register and then call one of the system calls and use it. Now, just like before, there are several classes of these system calls. One of them is the process control, and this involves creating the process and terminating the process, also ending it or aborting it, loading and executing it, getting process attributes and setting the attributes, waiting for a certain period of time or an event or signaling an event, allocating and freeing up memory, dumping the memory if there's an error, a debugger for determining if there's bugs in a single-step execution, and also locks for managing and accessing shared data between those processes. Another class is file management, so if we have to create or delete a file, do we need to open and close these files, read and write and reposition, get and set file attributes? Device management is another class, requesting a device, releasing that device, read, write, and repositioning the device. Get the device's attributes, setting the device's attributes, and logically attaching or detaching those devices. Another class of system calls is information maintenance. So getting the time or date, setting the time or date, getting the system's data and setting the system's data, get and set the process, file, or device attributes. Communication, being able to create and delete communication connections, send and receive messages if you have a message passing model. Now, if you have a shared memory model, this is to create and gain access to the memory regions. Also, we need to know the transfer status information of this communication and also attach and detach remote devices that are communicating. And finally, protection. This controls the access to those resources, getting and setting the permissions to be able to access those resources, and also allowing and denying user access. Here are some examples of Windows and Unix system calls. Now here's an example of some easy C code and showing how this can be used. Now remember, when we had talked in the previous class, The thing is, you have a distinction between user mode versus the kernel mode. So if you call the function printf with the string greetings, that accesses the standard C library, which then evokes the write command. This command is an operating system command. Once that's loaded and completed, it returns back to the user program. Now, moving on from system calls, we also have this other thing called system services, otherwise known as system utilities, and this provides a convenient environment for program development and execution. Now, some of these can be divided into file manipulation, status information, programming language support, program loading and executing, communications, background services, and application programs. Looking into this a little further, file management, we need to be able to create, delete, copy, rename, print, dump, list, and generally manipulate files and their directories. We need to know some status information. So we need to ask the system for like date and time, amount of available memory space, and other things. Going even further, file modification like text editors to create and modify these files, special commands to search for the contents of the files and perform transforms on the text. Programming language support. We need compilers, assemblers, debuggers, and interpreters that are provided or should be provided with the operating system. Loading and executing a program, and also communications between the programs. So we got to provide a mechanism for creating these virtual connections between and among processes. Some of the background services, this is what happens when we launch at boot time. And it provides like disk checking, process scheduling, error logging, printing, all that kind of stuff. These are also known as services, subsystems, or daemons. And finally, we have application programs that don't pertain to the system and they're run by users. These are not typically considered as part of the operating system, and these can be launched by command line, mouse click, or finger poke. In relation to that, we also have linkers and loaders. Now, usually a program resides in disk as a binary executable file. To run this on a CPU, the program has to be brought into memory and placed into the context of a process. The source files are compiled into object files that are designed to be loaded into any physical memory location, a format known as a relocatable object file. The linker combines these relocatable object files into a single binary executable file. Now, during the linking phase, other objects and files or libraries may be included as well, such as the standard C or math library, which can be specified using the flag -lm. Now, a loader is used to load the binary executable file into the memory where it is now eligible to run on the CPU's core. An activity associated with linking and loading is relocation, which assigns the final addresses to the program parts and adjusts the code and the data of the program to match those addresses. Here's an example of the roles that the linker and the loader takes. If we have our source program right here, we then compile it using our compiler, and then that generates this object file here. Going further with this, we can then utilize the linker to generate the executable file. When we start running this executable file, the loader then loads this into your main memory, and those dynamically linked libraries are accessed when necessary. Now, as we're developing software, why are applications so operating system specific? Fundamentally, applications compiled on one operating system are not executable on another operating system. Now, based on some earlier discussion, we can see part of the problem. Each operating system provides a unique set of system calls. System calls are a part of the set of services provided by the operating systems for the use by applications. Even if a system call were somehow uniform, other barriers would make it difficult for us to execute application programs on different operating systems. Now, if we were to make an application available on multiple operating systems, there's a couple of ways to do this. One is the application can be written in what's called an interpreted language like Python or Ruby. The interpreter reads each line of the source program and executes an equivalent instruction on the native instruction set, and then calls the native operating system calls. Problem with this is performance suffers relative to the native applications, and the interpreter only provides a subset of each operating system features, possibly limiting the feature sets of the associated applications. Another approach is the application can be written in a language that includes a virtual machine containing the running application. The virtual machine is part of the language. One example of this is Java. Now, the Java includes a Java virtual machine and also a bytecode verifier and other components that need to be loaded into Java. Now, these type of systems have similar disadvantages as we discussed before with the interpreters. Finally, the application developer can use a standard language or API in which the compiler generates the binaries in the machine and the operating system specific language. The application must be ported to each operating system on which it will run. This porting can be quite time-consuming and must be done for each new version of that application with subsequent testing and debugging. Now that we have discussed many of the requirements involved with creating an operating system, now we move on to how we design and implement these systems. Now, the first problem in designing the system is to define the goals and their specifications. Now, at the highest level, the design of a system will be affected by the choices of hardware and the type of system. But beyond that, the requirements may be much harder to specify. The requirements can, however, be divided into two basic groups: user goals and system goals. Users want certain obvious properties in the system. The system should be convenient to use, easy to learn and use, reliable, safe, and fast. Of course, these specifications are not particularly useful in the system design. Now, a similar set of requirements can be defined by the developers who must design, create, maintain, and operate the system. The system should be easy to design, implement, and maintain, and it should be flexible, reliable, error-free, and efficient. But again, these requirements are fairly vague. In short, there's no unique solution to the problem of defining the requirements for an operating system. Before we go forward, we need to discuss policies and mechanisms. Policies are defined as what needs to be done. The mechanism is how we do it. It is important to separate these two out. The separation of a policy and a mechanism is important for flexibility. Policies are likely to change across places or over time. In the worst case, each change in a policy would require a change in an underlying mechanism. A general mechanism that's flexible enough to work across a range of policies is preferable. Now, in order to actually create or implement the operating system, we kind of need to take a look at how they were originally made. Early operating systems were written in assembler language, and now most are written in either C or C++ with some small amounts of assembler. Now, as we're still discussing design and implementation, we need to take a view at the operating system structure. A system as large and as complex as a modern operating system must be engineered very carefully if it's to function properly and to be modified easily. Now, there's various ways that we can structure this, and we can go from simple structures like MS-DOS to vastly more complex like Unix. We can also take a layered approach and also a microkernel approach. Now, looking at each one of these one at a time, the simplest structure for organizing an operating system is no structure at all. That is, we place all of the functionality of the kernel into a single static binary file that runs in a single address space. Now, this approach is known as the monolithic structure, and it is a common technique for designing operating systems. The original Unix was a monolithic structure. In this case, the kernel consists of everything below the system call interface and above the physical hardware. It provides the file system, CPU sharing, memory management, and other operating system functions. A large number of functions for one level. This is the way that we can view the Unix system structure. Now, the monolithic approach is often known as tightly coupled systems because changes to one part of the system can have wide-ranging effects on other parts. Another way we can look at this is we could loosely couple the system, such that the system is divided into separate smaller components that have specific and limiting functionality. Now, a system can be made modular in many different ways. One of those is called the layered approach, in which the operating system is broken into a number of layers or levels. Layer 0 is the hardware layer, and then it goes through a series of layers till it gets to layer N, and that is your user interface. The main advantage of this style of approach is it's simple to construct and debug the operating system. One important aspect of the layered approach is each layer is implemented only with the operations provided by the lower levels. A layer does not need to know how these operations are implemented. It only needs to know what they do. Therefore, each one of the layers hide the existence of certain data structures, operations, and hardware from the high-level layers. This has been successfully used in computer networks and web applications. However, very few operating systems use a pure layered model. One reason for this is the challenges of appropriately defining the functionality in each one of the layers. In addition, the overall performance of the system is poor due to the overhead of requiring a user program to traverse through multiple layers to obtain an operating system service. Now, taking a fairly different approach, we could explore microkernels. And the method for these structures basically removes all of the non-essential components from the kernel and implement those as user-level programs that reside in a separate address space. The result is a very small kernel. One benefit of a microkernel approach is that it makes extending the operating system very easy. All of the services are added to the user space, and consequently do not require modification of the kernel itself. One of the best known illustrations of a microkernel operating system is Darwin, the kernel component of the Mac OS and iOS operating systems. Now, unfortunately, the performance of a microkernel can suffer due to increased system function overhead. The overhead involved copying messages and switching between processes has been the largest detriment to the growth of microkernel-based operating systems. Here's an example of how you can view a microkernel operating system structure. Now, arguably, one of the best current methodologies for operating system design involves using loadable kernel modules, LKMs. Now here, the kernel has a set of core components that can link in additional services via modules, either at boot time or during runtime. This type of design is common in modern implementations of Unix such as Linux, Mac OS, and Solaris, as well as Windows. The idea of the design is for the kernel to provide core services while other services are implemented dynamically as the kernel is running. Now, the overall result resembles a layered system in that each kernel section has defined protected interfaces, but it is much more flexible than the layered system because any module can call any other module. The approach is also similar to the microkernel approach, in that the primary module has only core functionality and knowledge of how to load and communicate with the other modules. But in this case, it's more efficient because the modules do not need to invoke message passing in order to communicate. Linux, for instance, uses loadable kernel modules primarily for supporting device drivers and file systems. Now, in practice, very few operating systems adopt a single strictly defined structure. Instead, They combine different structures, resulting in a hybrid system that addresses performance, security, and usability issues. Going further into implementation, it is possible to design, code, and implement an operating system specifically for one specific machine configuration. But more commonly, operating systems are designed to run on any class of machines with a variety of configurations. If you are generating or building an operating system from scratch, you need to follow these steps. You have to write the operating system source code. You need to then configure the operating system for the system it will run on. Then we must compile the operating system. Then install the operating system. Then boot the computer with the new operating system. Now, after an operating system is generated, it must be made available for use by the hardware. But how does the hardware know where the kernel is or how to load it? The process of starting a computer by loading the kernel is known as booting. On most systems, the boot process proceeds as follows. First, a small piece of code known as the bootstrap program or bootloader locates the kernel. The kernel is then loaded into memory and started. The kernel then initializes the hardware, and then the root file system is finally mounted. Some computer systems use a multi-stage boot process. When the computer is first powered on, a small bootloader located in the non-volatile firmware, known as the BIOS, Basic Input-Output System, is run. The initial bootloader usually does nothing more than load a second bootloader, which is located at a fixed disk location called the boot block. Many recent computer systems have replaced the BIOS-based boot process with a UEFI, a Unified Extensible Firmware Interface. Now, the UEFI has several advantages over the BIOS, including better support for 64-bit systems and larger disks. Perhaps one of the greatest advantages that a UEFI is a single complete boot manager, and therefore is faster than using a multi-stage BIOS process. Now, sooner or later, it starts the operating system and mounts the root file system. It is only at this point does the system said to be running. Grub is an example of an open-source bootstrap program for Linux and Unix systems. Boot parameters for the systems are set in the grub configuration file, which is then loaded at startup. Now finally, bootloaders for operating systems including Windows, Linux, Mac OS, as well as both iOS and Android provide booting into recovery mode or single user mode for diagnostics. This can be good for figuring out what's going wrong with hardware, fixing corrupt file systems, and even reinstalling the operating system. Now, going beyond that, we have already mentioned debugging from time to time, but now let's take a closer look about debugging an operating system. Now, broadly, debugging is the activity of finding and fixing errors in a system, both in the software and also in the hardware. Performance problems are considered to be bugs as well, so debugging can also include performance tuning, which seeks to improve performance by removing process bottlenecks. If a process fails, most operating systems write an error to a log file to alert the system administrator or users that a problem has occurred. The operating system can also take a core dump, and this is a capture of memory of the process and store that in for files for later analysis. Now, to distinguish this, a failure in the kernel is called a crash. When a crash occurs, error information is saved to a log file, and the memory state is saved to a crash dump. Now, moving beyond crashes, performance tuning can optimize the system's performance. Now, one mechanism to do this is called a counter. And operating systems keep track of system activities through a series of these counters, such as the number of system calls made or the number of operations performed to a network device or disk. Now, going beyond that, a counter-based tool simply just inquires on the current value of a certain statistic that is maintained by the kernel. However, tracing tools collect the data for a specific event. such as the steps involved in a system call invocation. These listings are great to record and analyze when things go wrong. One famous quote is called Kernighan's Law, and Kernighan's Law states, "Debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are, by definition, not smart enough to debug it." Now, this chapter has focused on the requirements of creating an operating system, the designs of an operating system, and how we may implement it. And with all that being said, I'll see you next time.